Okay, we'll start. Just be waiting there another 2 minutes. Okay, in this class, what I'll do is I'll take up the frame analysis of rigid jointed frames by stiffness method. Okay, so we have seen in case of beams. Only thing is we had not touched the problem of settlement in beams. Okay, settlement. What you have to do, you need to consider that moment due to settlement minus xci delta upon L square. So that has to be taken in the fixed end moments. I think the same you have done it in Kani's method as well as moment distribution method. Okay, so like that, your P dash matrix will be containing that moment due to settlement over there. Okay, so that should be in that matrix over there. Okay, so at present, I'll go with the frames. Later, if you try solving that one, in case any difficulty is there with that, I'll take up that also. Okay, so I'll take a frame. Okay, so rigid jointed frame. So this is the frame what we have here. Okay. You can please write down this problem solution because I'll try to provide it later, but right now I don't have it. I'm solving right here only. Okay, so the load, let's see, it's 20 kilonewton per meter, and this is 40 kilonewton. Okay. And this is 60 kilonewtons. Okay, and this is joint A, support A, you can also call it B, C, and D over here. Okay, I hope you are able to see the screen and the audio is audible. Distances are 2 meter, 2 meter. This is having the moment of inertia of 2i. Here also the moment of inertia is 2i, and for this it is I, and this is 2 meters. Okay, and this member BC is of 5 meters. Okay, so this distance is 5 meter. Okay, so here when we begin with the solution, we start with identifying the degree of kinematic indeterminacy. Okay, So the first step in our solution is what is the degree of kinematic indeterminacy in this case, in the speed or in this frame here, right? So we have four joints. At each joint, there are three possible displacements, okay? Rotation and two translation. Translation in x direction and translation in y direction. There can be a rotation at a joint, translation, movement of the joint in x direction, displacement of joint in x direction, you can also call it, and the joint can also get displaced in y direction, okay? So in this, here you can either go with the formula, okay, that is each joint 3j, 3 displacement are possible, minus, if you have supports like this, the displacements are restrained, okay, at every supports the displacements are restrained, but restrained by what? Restrained by the reactions, okay. If I provide a hinge support, it will restrain the two displacements, translations in x and y, it will allow rotation, okay. So like that, whatever number of reactions will be there, so that will be the restraints applied on the displacement, okay. So you can write that as 3j minus r plus the number of inextensible members, okay, m. Axially, if the members are rigid, we'll consider them inextensible members, okay. So here how much it comes out? 4 into 3, it is 12, okay. So 12, or else 4 into 3, that is our 4 joints, sorry, 3 into 4, okay, minus total reactions are 3 plus 3, 6, okay. So 6 reactions are existing, plus all three of the members are axially inextensible, okay. That is axial deformation in these members AB, BC and CD are neglected over here. So what will be this equal to? 12 minus 3, 12 minus 9, so it comes out as 3, okay. So from this equation you can find out what is the degree of kinematic indeterminacy is, okay. That is one way. Or else what you can do is directly you can go for identifying in this structure itself. How I do that? Look at the joint. See, at A, no displacements are possible because it is fixed. So there is cannot be any translation. Translation in x direction is restrained. Translation in y direction is also restrained. And even the rotation is restrained. So no question of any displacements existing at joint A. Similarly, at joint B, there cannot be any displacements. Okay, but at joint E, there cannot be any displacements since fixed support is provided here. Okay, at joint B, there can be rotation, that is one displacement. At joint C also there can be rotation, that is another displacement, two independent displacement. In addition, this frame can sway. Okay, so these joints B and C, they can get displaced in x direction by equal amount. Okay, by equal amount. Whatever is the displacement of B, the same will be the displacement of C. Okay, so that is one more unknown displacement. So from that also immediately I can write what is my degree of kinematic indeterminacy. From observation also it will come out to be 3. Okay, so you can go either of the way, whatever is convenient for you. Either you can use this formula or you can go for identifying visually by visual inspection. So degree of kinematic indeterminacy, it is identified now. So here unknown displacements, okay. So once degree of kinematic indeterminacy is told, we can have unknown displacement here. We can write them theta B, theta C, sorry, this is theta C, C, okay, and delta, okay. Delta is the sway of the frame, right? So next what we are going to do is we are going to assign the coordinates for this frame, okay, reference coordinates. How we are going to do that? So here I'll choose the coordinates. So what will be my coordinate? I'll take the frame over here, okay. Okay, then right. So this is the frame what I have. Now I have to give the coordinates. So here we have the support, and at this point also I have the support. So now the rotation at B, okay, rotation at B will take as the first coordinate. Okay, for that displacement we will assign the first coordinate here. Okay, so since it is rotation, we will have to choose between clockwise and anti-clockwise. So we'll assign a clockwise coordinate at B for the first unknown displacement theta B. Then for C, next I'll move to assigning the coordinate for rotation at C. That is one more unknown displacement. Here also I'll choose the coordinate direction as clockwise. Since there is an unknown rotation taking place at B and C, I've chosen two clockwise rotations. These are the coordinates what I have chosen at B and C. Okay. The next one is this translation or displacement. Okay, which is sway. Okay, what I have. So for that, what I'll do is I'll assign a coordinate over here. Since it is same at B and C, whether you assign this coordinate at joint B or joint C, that doesn't matter over there. Okay, so as long as it is the same, this one displacement. So here I'll assign this coordinate. Okay, at joint B, I have taken the third coordinate, right? So these are my coordinates now. So this is coordinate number 1 at B. They are usually put in numbers in circles. Okay, coordinate 2 at C and coordinate 3 again at B, but in horizontal direction. Okay, these are the three coordinates what I have. Now once I have the coordinate, the next thing what I'll do is I'll put my displacement matrix here. So what we'll do is we'll write this displacement matrix, which is delta, represented by delta. So this delta, okay, what it consists of? The unknown displacements which we have identified here. Okay, so in first coordinate theta B, in second coordinate what I have is theta C, and in the third coordinate it is delta sway. Okay, so these are my unknown displacements. Okay, so that is the first matrix what I have got here, displacement matrix. Now after writing this displacement matrix, now what I'll have to do is I'll go with getting or developing my force matrix. Which force matrix? P dash matrix. Okay, so the force matrix here. Okay, so this is force matrix and this is P dash here. Okay, so how do I obtain this P dash? P dash can be obtained by arresting all the displacements in the coordinate. I'll restrict all the displacements in the coordinate. Means I'll make these two joints, okay, B and C fixed, okay, because there are displacement taking place at B and C, where here at joint B and joint C. So I'll just fix them, okay. I'll assign a fixed support for this joint B. That is now this BC member will be a fixed beam. Same for member AB. I'll make the two ends as fixed, and also for member BC. Okay. So what happens once I do that? We have to calculate these fixed end moments. So these will help in determining the P dash matrix or the elements of the P dash matrix here. Okay. So can anyone calculate them and tell me what are these values? So these ends, they are not allowed to displace in any direction. They have been restrained now. Okay. So we are providing the fixed support at all in all our coordinates. Mainly we want to restrain the displacements in the coordinates here initially. Okay. So now my displacements in the coordinates have been restrained. So that is at B and C, the coordinates were there. So at B and C, we have put the restraints here now. The other loads which were there, they'll be as it is. Okay. Now, when you are working with P dash matrix, you are mainly finding the forces which are developed in the coordinate due to the applied loads. Okay. So here, this is my member AB. Okay. So you have to determine what are the fixed end moments in member AB and in BC as well as in CD. Okay. If you find those fixed end moments, then we can calculate the P dash matrix elements. Okay. So what is this P1 dash? It is the moment in the first coordinate. Okay. P1 dash represents what is the moment in the first coordinate, because first coordinate is corresponding to what, the rotation here. Okay. First coordinate. Second coordinate is also corresponding to rotation. Okay. So I want to know what moment is there in first and second coordinate due to the loads which are present on the member here. Okay. So here what I have, this UDL, it is 20 kilonewton per meter, and this is 60 kilonewton. Okay. So these are the loads which are present on the member. Okay. This 40 kilonewton load, it is applied in the coordinate number 3. Okay, at joint P coordinate number 3. So this is coming in coordinate, not on the member. So this will be taken in the coordinate. Okay, this will come in a different force matrix. So here in P dash matrix, this will not come. The force which is directly applied in the coordinate will not come over here. So here what you have, the moments will be developed. So can you find out those values over here? These are the fixed end moments what will come across in this beam, and also over here in the member AB, these are the fixed end moments what I have. So in this member CD, since loading is not present, the fixed end moments will also become 0. Okay. So in member AB, so this is 2 meter and 2 meter, WL by 8 minus WL by 8 minus 60 into 4 by 8. How much it comes out? 60 into 4 divided by, that is 60 by 2. So this will be 30.
30.
Okay, 30 kilonewton meter, and this will also be 30 kilonewton meter. What about this reaction? These two will be equal, and they will also be half of the 60 kilonewton. So these will also come out to be 30 kilonewton and 30 kilonewton. Okay, to find this reaction, actually I have to consider moment about A. Okay, so this is minus 30 anti-clockwise plus 30 anti-clockwise cancelled. Okay, and then 60 into 2, everything divided by 4. Okay, that is, this member free body diagram should be taken along with these fixed end moments, and then you should go for determining the reactions. Okay, so that will be the reaction. Since this two moments are same, they will cancel each other. I'll get directly as 60 into 2 divided by 4. Okay, see, if I call HA and HB, so this is HA, okay, and this is HB, the two reactions at the joints A and B. So if I take moment of all the forces about A over here for determining the reactions, if I take moment about this joint A, okay, then what it comes out here, this HB, okay, HB into 4, it will be anti-clockwise, okay, for the direction what I have assumed, minus this 30 kilonewton moment which is directly at A, minus 30 kilonewton meter. Then there's one more moment at B, which is in clockwise direction, plus 30 kilonewton meter. Okay, should be, and plus one more is the 60. Due to 60 kilonewton, the moment is clockwise. 60 into 2 meters should come out to 0. Okay, this equation will tell you what is hp equal to actually. Okay, this is how you should go for determining the reaction at the supports a and b. They are required in our case. Okay, we'll see that. But here in this case, when this 30 and 30 minus 30 plus 30 gone, so what I have is HB will be equal to 60 into 2 by 4. Okay, 60 into 2 by 4. That's why it is coming out to be 30 kilonewton here. Okay. So, like you do for other beams, for that purpose, we require these reactions. That, like you solve the beam problems, in the same way, you have to obtain these reactions, considering the fixed end moment and the applied load. Okay. Now, what I have, I want to find out the fixed end moments next. I am done with member AB. Okay, the moments and fixed end moments and reactions are determined. What about member BC? What is the fixed end moment here? WL square by 12. Okay, so 20 into 5 square by 12.
41.67.
It is
41.67.
41.6.
okay, 41.6. Right. So here it is 40, 41.67, and this should also be 41.67. Okay, so these are the fixed moments. These two are 0 and 0, no load is there. Right. Now what I'll do is I'll go for finding what is my P1 dash first. P1 dash will be equal to here at joint B, where my first coordinate is there. First coordinate corresponds to rotation. So I'll be finding the total moment at joint B. It will be equal to MF BA plus MF BC. Okay, so what it comes out, MFBA is 30 clockwise, MFBC is 41.61 anti-clockwise. So 30 minus 41.67, or P1 dash will be 11.67.
67.
Okay, so this is 11.67 kilonewton meter. Okay, similarly, what about P2 dash? P2 is here. It will be for MCB plus MCD. Okay, P2 dash will be equal to, this also corresponds to a rotation. So I'll be finding what is the total moment at joint C due to the load supplied on the member. Okay, so it is given by MFCB plus MFCD. Okay, so this is MFCB is 41.67 clockwise moment plus MFCD is 0. So P2 dash, what I get is just 41.67 kilonewton meter. Okay, so this is what you have. Now one more is third coordinate. So here what you have is P3 dash. Okay, what is this third coordinate? We have taken third coordinate as a translational coordinate in the horizontal direction. Okay, so you should be looking for any concentrated force which are coming in the third coordinate. Okay, so concentrated force due to the loads applied on the member. Okay, due to the loads applied on the member, not due to the loads which are applied in the coordinate. Okay, so because of the loads which are applied on the member, we came across some reactions over here at A and B. Okay, so in at joint B, I have a reaction, okay, in the direction of this coordinate. Okay, maybe it is opposite in direction, but it is in this coordinate 3. What is that? 30 kilonewton. So P3 dash is nothing but P3 dash is this horizontal reaction at B, HB, which is equal to 30, but it is in opposite direction to our coordinate. So minus 30 kilonewton. Okay, P3 dash. That is what my P3 dash is. Or if I put everything over here in this P dash matrix, what I have, it will be equal to what? P1 dash, which is 11.67, P2 dash, P1 dash was minus 11.67, So this is also minus 11.67. And what is this? P2 41.67 and P3 is minus 30. Is that correct? What I have done here, calculation? Just verify. Okay, so I have my P dash matrix. Okay, so if that is fine, we'll move ahead. Is there any confusion in that part? Okay, so I'll come to the next part over here. In next part, what we are supposed to do is we'll be going for developing the stiffness matrix. Okay, so stiffness matrix. Okay, this is our stiffness matrix. It is a square matrix and a symmetric matrix. Okay, so for developing the stiffness matrix, again, we'll be taking up that frame. Okay, so this is the frame that I have. So what I should do for developing the stiffness matrix is start applying unit displacement in the coordinate one by one and find the forces in the other coordinates. Okay, so first is I'll take the first coordinate. Okay, I'll give unit rotation in the first coordinate and without giving any displacement or rotation in second and third coordinate. So I'll have to restrain the displacement in second coordinate. Okay, and in the third coordinate, I'll see that there is no translation of the frame and there is no rotation at C where my second coordinate is there. Okay, with that what I'll do, I'll give unit rotation in the direction of first coordinate. First coordinate was in clockwise direction, so I'm giving a unit rotation in clockwise direction in my first coordinate. Okay, so when I do that, I have to rotate two members by one unit. Okay, so these members BA and BC are meeting at this coordinate. Okay, so I'll be giving this unit rotation here. Okay, so this is, if you draw a tangent over here, so these will be having one radians slope or one unit slope here. Okay, that is what unit rotation is. So here this is the unit rotation, one unit and one unit. Okay, so A, B, C and D. Okay, properties what we have is I,
दादा कोण आहे
okay, this is I for member CD, 2I for member BC and 2I for member AB. Okay, what are the lengths? This is 5 meter, 2 meter and 4 meter for this. Okay, so K11, what is the force in the first coordinate due to unit rotation in first coordinate? It is given by 4 EI by L over here. Okay, so in this case 4 4EI by L for BA and 4EI by L for BC. 4E into 2I because it is having moment of inertia 2I divided by 4 plus for member BC it is 4E into 2I, that is also having moment of inertia as 2I, okay, divided by what? 5 meters. So this divided by 5 meters. So what this comes out, and at the same time if I go for finding what is the force in the second coordinate, that will be K12 2EI by L. It is given by 2EI by L. So it will be 2E into, for member BC it is 2I divided by 5. Okay, so what this comes out as, and in the third coordinate, okay, K13 force in third coordinate when unit displacement is given in first coordinate, it will be minus 6EI by L square. Okay, so here there will be a reaction what will be developed here at B. Okay, when I apply a moment for rotating these members about joint B. Okay, E and I are for this member AB. Okay, the member AB. You should take the E and I values of this member AB. So I can here write for member AB, properties of AB here. Okay, so here what it comes, minus 6E into 2I divided by 4 square here. Okay, so I'll just show you this vertical number. If you take this, okay, and when you apply a rotation here, okay, a moment over here, what happens is there will be a reactions developed over here at these points. These are given by 6EI by L square. Okay, this member will not affect because what reactions are developed in vertical direction in member BC. Our coordinate is horizontal direction. Okay, third coordinate. So I'm looking for any force which are developed in the third coordinate. So only member AB will offer that forces in third coordinate. So how much that this comes out? Can you give this value? 444. Okay, 5 to 10 plus 8. 18 over EI.
18 by 5 EI
Okay, 18
by 5
right.
EI by 5.
Is that correct?
Yes.
For this it will be 4 EI by 5. K12. And this one will be minus 12 by 16. How much that comes out?
0.75.
0.75. Okay, minus 12 by 16. 0.75. Or it is 3 by 4. 3 EI by 4 minus 3 EI by 4. Okay, so this is what we have. Sorry, this is correct, 4 meters. Huh? Okay, K13 is 4 meters. 6 EI by S square. For AB it was 4 meters, right? What we have taken? Okay, 4 meter, 2 plus 2, 4 meter. Right, these are the values of stiffness coefficient, what we obtain here by giving unit displacement in first coordinate. Now what I have to do is, we'll move on to the second coordinate here. Okay, so at second coordinate also what I'll do, I'll give unit rotation. I'll give unit displacement in the direction of the coordinate. Okay, and go for calculating what are the forces in all the other coordinates over here. So this is the frame again. Okay, and here we have one more member. This time what I should be doing is I'll be giving unit rotation in second coordinate. You can proceed further if you are calculating. So here there should not be any displacement or rotation given in the first coordinate. So we'll restrain all the displacement in first coordinate. That is, I don't want to have any rotation or translation in first and third coordinate. Sorry, this will be clockwise, right? Correct, clockwise. So I have to give a rotation in the direction of the coordinate. So here again I have to rotate two members for giving unit rotation in second coordinate. Okay, so these two are the rotations what we have in the second coordinate. So this is 1 and 1. Okay, so these rotations are 1 unit in second coordinate. Now what I'll do is I'll go for calculating what is my stiffness coefficient K22. Again, this is given by 4 EI by L. Okay, so what is this 4 EI by L? It should be applied for member CB and CD. Okay, so A, B, C, and D. Okay, so we have the properties here, same are there. So for CB, 4E into 2I divided by 5 plus for CD it is 4E into I. Okay, moment of inertia is I here for CD divided by 2. Okay, so this is 1. Next, we have already calculated K12. It is not required to calculate K21. Okay, I'll go for calculating what K23, force in the third coordinate when unit rotation is given in second coordinate. K23, what will happen for this? Okay, when I apply unit rotation over here, right, what is the force developed in the third coordinate? That should be known to me. How much will be that force developed in the third coordinate? So third coordinate is over here at joint B. Okay, that is the translational coordinate. Okay, so how much will be the force over here? So what you have is so here the third coordinate force. Actually, I want the force in the third coordinate here. So if I take this third coordinate, this comes out to be 0. Okay, the force in the third coordinate due to unit rotation in second coordinate. Okay, so I'm not getting any force at joint B where my third coordinate was there. There will not be any force in horizontal direction over here at joint B. So for that purpose, K23 will be 0. Okay, so this is what is required. K12 or K21, we already have it, the value 4 EI by 5. So it is not required to find out K21 again. Okay, the K12 and K21 are equal. That is the property of symmetric matrix. Okay, K23 is 0 because at joint B there will not be any force coming over here. There will not be any reaction coming at joint B in this case. Okay, so after that, the next job is to give unit displacement in the third coordinate. So what is the how much is the unit displacement? Just a minute. How much is the force required for giving unit displacement in third coordinate? If that is determined, that will be our K33 over there. Okay, so what I'll be doing is first I'll go for applying unit displacement in third coordinate without giving any displacement in first and second coordinate. Okay, so in first and second coordinate you have to prevent the rotations. Okay, keeping first and second coordinate fixed, you have to apply unit displacement in third coordinate. So you have to push this frame by 1 unit in the direction of the first coordinate and do not allow any rotation in second and third coordinate. So this is 1 unit. I have pushed it by 1 unit. 1 unit translation is given over here. So that will result in displacement at B and C, both the joints. So this is A, this is B, this is C, and this is D. Okay, 1 unit rotation is given. So 4 meters, 2I, this is 5 meter, and 2I, 2 meter, and I. Okay, so what is K33? I only require K33 in this case. K33 will be 12 EI by L cube. It is given by 12 EI by L cube. Okay, so here you have to push two members. One is BA and another is CD. Okay, so these two members have to be pushed by 1 unit. So 12 EI by L cube for member AB or BA, 12 E into 2I by 5. Sorry, what is the length? 4 meters, 4 cube. Okay, plus 12 E into I for member CD divided by 2 cube. Had anyone calculated these values? I want this K22 value. How much will be this? 4 plus 2, 8 by 5, and this will be again 2,
18 by 5. 18 by 5 EI.
18 by 5 EI. 18 EI by 5. Okay, so this is one. Okay, now what about this one? So how much this comes out to be? K33. Even you can verify this K32, which is equal to K23 also here also. So due to this way, there is no moment set up in this beam. Okay, so this is 0. Okay, this way this displacement is not affecting. Minus 6 EI delta by L square. Actually, it is given by, in this case, minus 6 EI delta by L square. Here delta is 1. Okay, or for this member BC, delta is 0. Okay, so since it is 0, we have given unit displacement for member AB, these vertical members AB and CD. So sway will be affecting only the columns. So beam, nothing will happen due to sway. So movement set up in that member beam at joint B will be 0. That is another way of calculating this K value, 2, 3 or 3, 2 value. Okay. So can you tell me what is K33 equal to? So this is 24 by 4 cube,
15 by 8 EI. 15 by 8 EI.
15 by 8 EI.
EI.
Okay, okay. So this is 15 EI by 8. Okay. So now I can write the stiffness matrix here. So what will be the stiffness matrix? You have to arrange them over here. Okay. Is that okay? The calculations, others, the values, if you have calculated any differences there, tell me. If not, we'll go ahead with this stiffness matrix. So these are our values, what we have here. So what I have, first one, EI is common for everything. So I'll keep it outside. K11, how much was K11? We had it as K11, 18 by 5. Okay, so what is this 18 by 5? If I just divide it, let me put it in decimal. So it comes out to be 3.6. This is 3.6. Okay, and what about the K1 to 4 by 5. So 4 by 5 is coming out to be 0.8. Okay, so this is 0.8. What about K13? It is minus 3 by 4. Okay, so minus 3 by 4, it is minus 0.75. So minus 0.75. Okay, 75 over here. Okay, so that is our first row of the stiffness matrix. Is that okay? The values what I have taken after dividing. So this column, first column will be same as first row. So directly I can put 0.8 minus 0.75. Okay. What about K22? K22 was equal to 18 by 5. So again, it is same as K11. In this case, we are getting it as same. And K23, 32, they are 0. And we have K33 as 15 by 8. So 15 by 8 is 1.875. So this is my stiffness matrix. Okay, you agree with me? Anybody if have verified? These are my stiffness matrix here. If you have the same, then any other answers, please tell me. Okay, so now what we have is equilibrium condition. We will go for applying the condition of equilibrium. So what was our condition of equilibrium? Net force. Okay, net force in the coordinate is P. Okay, is given by force due to the displacements in the coordinate plus the force due to the applied loads on the member. Okay, in turn, this was K into delta stiffness matrix into the displacement matrix was P delta plus, sorry, this is P dash. Okay, P dash. Sometimes I use PL also. So it is P dash over here. So this is P dash, right? Now what about the P matrix? Okay, force matrix, P matrix. So what we have is P1. If you look into the original frame, so there is no force which is directly applied in first coordinate. There is no moment which is coming in the first coordinate at B. First coordinate is at B, so there is no force at B in the first coordinate. There is no moment which is there at B in the first coordinate. Okay, so P1 is 0. Similarly, in second coordinate, which is at joint C, there is no moment which is directly applied in the second coordinate. So P2 is also 0. Okay, but if I take the third coordinate, okay, which is here, and compare it with my frame which was given to me, there is a force in the direction of first coordinate. There is a force which is applied in the third coordinate. Sorry, there is a force which is applied in the third coordinate. It is 40 kilonewton concentrated load which is there. So this 40 kilonewton concentrated load is directly acting in the coordinate here. Okay, so P3 will be having a value of 40 kilonewton. Okay, P3 value will be 40 kilonewton. Okay, so what I have is I can write P1 is equal to 0, P2 is also 0, so P2 is also equal to 0, and P3 will be 40 kilonewtons. P3 is 40 kilonewtons. Okay, so this gives me my P matrix. Okay, so I'll just put all the matrices over here. So this is 0, 0, and 40. So which is equal to EI, okay, into our stiffness matrix 3.6, 0.8 minus 0.75, 0.8 minus 0.75, 3.6, 0, 0. Okay, and here it is 1.875 into the displacement matrix where theta b, theta c and delta are there, okay, plus the p dash matrix. What was p dash matrix? Values were minus 11.61, 41.61 and 30. So minus 11.67, 41.67 and minus 30. These were the values in this p dash matrix. So can you rearrange this and get what is theta b, theta c and delta? Okay, so first matrix 3 by 3. So what I have 3.6, 0.8, minus 0.75. Okay, second row 0.8, 3.6 and 0, and this is minus 0.75, 0 and 1.875. Okay, second matrix what we have. So if I just take it on this side, directly I can write that value. It is a 3 by 1 matrix. It is 11.67, okay, minus 41.67 and 40. Okay, what will be that? 40 plus 30, 70. Please calculate. I'm trying to calculate. So matrix A inverse into matrix B. Please tell me what will be this if you have calculated. Minus 40. This will become plus 40 plus 30, 70. Okay. The values what I am getting here. Okay. For this, I have 15.67 by EI. That is theta B. Theta B is 15.67 over EI. And theta C, I have minus 15.05. Minus 15.05 by EI. And delta is 43.60 over EI. Okay, see what you will get. So these are my values what I have in my calculation. Tell me if any difference is there. Okay, once you have them, what you have to do is go for calculating the final movements over here. Okay, so MAB is equal to MF AB plus 2 EI by L into 2 times theta A plus theta B minus 3 delta upon L over here. Okay, so in this case we had minus 30 plus 2E into 2I divided by 4 into 2 into theta A was 0 because it was fixed end. And what is theta B? It is 15.67. Okay, so plus 15.67 15.67 over EI minus 3 by 4, 3 by L into delta is 43.60 into 43.60 over EI. Okay, this will get you the value of MAB. Similarly, MBA will be plus 30 plus 2E into 2I divided by 4 into 0 plus 2 times theta B, that is 2 into 15.67 over EI minus 3 delta upon L. Okay, 3 into 43.60 by EI into 1 by 4. This will be our MBA. And MBC, what we have is minus, what is the value of MFBC? Minus 41.67 minus 41.67, okay, plus 2E into 2I divided by 5 into 2 times theta B, which is 15.67 by EI plus theta C. Okay, so I think theta C is negative, so plus what is the value? Minus 15.05. Okay, minus 15.05 over EI. Okay, minus 3 by 5 into 0. Delta is 0 for this member. Okay, and MCB is 41.67 plus 2EI. Okay, 2E into 2I divided by 5 into 15.67 by EI. Okay, 15.67 by EI minus 2 into 15.05. Okay, this is 15.05 over EI minus 3 by 5 into delta is 0. Okay, this one. MCD will be 0, MFCD plus 2EI by 2 into 2 times theta C. Okay, so 2 into minus 15.05 by EI. Okay, plus theta D is 0 because it is fixed, and minus 3 delta by L. Okay, delta is how much? 43.60 over EI. So this is for MCD. And finally MDC, which is MFDC 0 plus 2 EI by L into theta C minus 15.05 divided by EI plus 2 times theta D 0 minus 3 delta 43.60 by EI, okay, upon L, which is 2 meter over here. Okay, so these are the final moments. Anybody have the value for this? Calculation. And maybe how much it comes out?
Minus 47.03.
Okay, 1 minute. Minus 47.03. Okay, what about the MBA?
28.64.
28.64. And what about MBC?
Minus 28.64.
Minus 28.64, exactly it is coming out. Okay, then MCB. M
30.126.
30.126.
okay 30.126 kilometer meter and MCD
Minus 95.5.
MCD. Okay, you are getting minus 95, but
Yes, sir.
that will not be cancelling MCB. Is that okay? All our calculation. That should not be like that. It is okay. So here, what you got? That should be minus 30 only, somewhere around minus 30. MF CD is 0, MFPC is also 0. Okay, 2 EI by 2 meter was the length, 2 EI by L, MFCD 2 times theta C plus theta D minus 3 delta by L. Okay, so please check that calculation once again. Okay, you just verify those multiplication and see what you get. Okay, done. So this is what you have in the frame analysis. Okay, the frame, so how you are going to take it. Okay, so we'll finish. Just try with this calculation, checking the calculation one more time. I'll see what correction is there in that also. Yes, Argavi raised your hand. Dakshat.
Sorry, sir, by mistake.
Okay. Okay, you can put the attendance in the chat box and we'll finish the class over here. Okay. Let us see what is the problem in that. After putting, please exit. Check the calculation of MCB also. If you are given the attendance, you can leave. Okay, we'll finish, we'll end it.